Hello and welcome back to Calculus 3. This is the part 3, even though the video says part 2 of the lecture. It's a very long lecture with limits and continuity. We reviewed Calc 1 limits, then we did Calc 3 limits, the 3 different kinds. One you can just plug in, one at the boundary, and then the limit does not exist with a 2 path. And now it's finally time to do continuity. Continuity. So this will be done the same way as in Calculus 1. We define continuity at the point and then so on. So we start with the continuity at the point. So that's a definition. So the function f of xy is continuous at a point AB, which is in the domain, in xy plane, provided, and we have the same 3 rules like in Calculus 1. Rule number 1, f of AB exists. This means that you are able to compute the value using pre-calculus. You just plug in the number. Let's say you have 2, 1 as a point. You plug 2, 1 in the function and it's going to give you a finite value. Number 2, limit as xy goes to AB of f of xy exists. So the limit needs to exist. And third one is that 1 is equal to 2. So the value you get in 1 is the same as value you get into 2. So that's that the limit xy goes to AB of f of xy is going to be f of AB. So this is standard definition. As you can see, it's identical to one in Calculus 1. So now we can say that global continuity is going to be given by if the function is continuous on every interior point, it's going to be right, because interior points are in the set of the domain. Those will be, then the whole thing is continuous function. So let me see if we can work on an example here. Sometimes they provide those extra examples to work on. Okay, I have to pick something from homework. So continuity, let's check. So let's do 34 first. Oops. 34. fxy is equal to xy divided by x squared y squared plus 1. Is this continuous? Right? We are trying to check continuity. Well, the only point or a line or something that could ruin our day would be when denominator is equal to 0. Do we see that? Because in that case you would have that wall, a plane that serves as a vertical asymptote of a sort, right? So 0, and the solutions to that are not real. If it was a -1, yeah, we have something to work with. But since it's +1, there's nothing we can do. So we say x squared, y squared plus 1 equals 0, and we just say no real solution. So this statement, no real solution, means there are no problem points, right? That means equal, no problematic points. And then all of that says continuous. If you have something as a problem 33, which is something polynomial-like, well, we know that's continuous everywhere. We should have some kind of denominator that would create issues. So now we're going to take a look at 36. Completely different story. Function s of xy is given as 2xy divided by x squared minus y squared. So now, if we are to do continuity, check, set denominator equal to 0. That would be x squared minus y squared equal to 0. Y squared equals x squared. And when you square root both sides, please don't forget plus minus. Y equals plus minus x.
Should we do that to the y as well?
What do you mean to the y?
Shouldn't we also do a plus or minus to the y?
No, just one is fine.
Okay, so one of them, does it matter which one we use?
No, you can put plus minus on either side,
Okay.
but only one side.
Okay.
So now, when we have this, if I draw a domain, which is our standard xy plane, I get to draw these two. I'll put them red. So we are looking from the bird's eye perspective. So continuity is lost on these walls. You can check that by looking at picking individual points and then running the three rules. You would see that any point you pick will ruin continuity because something within those three rules would break. So we were able to find in the domain the relationship between x and a y, which says that along these functions, these lines, continuity should fail. Now you can go and you can test this. If you test at 0, 0, most immediate, the first rule fails immediately, right? Because the function value doesn't exist. You have 0 divided by 0. That's not defined. Therefore, and that's not defined since it doesn't. It's not defined. Since it's not defined, it breaks the first rule. Continuity at 0, 0 immediately fails. But then, since x equals y, if you use plus, you can check point 1, 1, 2, 2, 3, 3, 10, 10, right? Any point you use to check continuity, it should fail. Now, in mathematics, we know that, and it's making the generalized statements is very dangerous. If you make any generalized statement in mathematics, you have to have a proof for that. So, if you want to disprove something, you just need one, because mathematics hates exceptions. There are no exceptions to any of the rules in mathematics anywhere. So when you say all, it's all, and there are no exceptions, no matter the circumstance, right? So what we have there is the function y equals x and then y equals negative x, along which we can pick any point and something will break. So as I said, if we pick 0, 0, and 0, 0 is on both of these lines at the same time, rule 1 fails. And no continuity, right? Immediately implies no continuity. If you pick 1, 1, again, rule 1 fails immediately, because you have 2 divided by 0, right? 1 squared minus 1 squared is 0. So immediately, again, no continuity. So picking any point along the lines that you found out over there will immediately make continuity fail. Is this continuous? No, it's not continuous. Great. The next order of business for continuity is to say that this book doesn't mention it, and they should, that the function is globally continuous, meaning everywhere, if it's continuous at all interior points of the domain. Because all of those a and b's that we are computing, they're all in the domain. And we don't care about the boundary, because boundaries are the edge. There is nothing to be continuous to, right? Does it make sense? So if you take a look at this keyboard for the computer, the whole keyboard, the entire thing is continuous, right? From one end to another end. I don't care about its continuity at the edge, because there's nothing to be continuous to, right? Now, for the connection over here, I need it to be attachable, right? So that I can attach it to the rest of the tablet, and then it becomes continuous with the tablet, right? And it also serves the purpose. So we define the global continuity for the entire object as if the function is continuous at every interior point of the domain, then the function is continuous as globally continuous. Because you can have, we can also define piecewise continuity, and that opens the door to other levels. Some of you will go to 300, 400 level math, and you will enjoy that there, all right? More details. So the next definition is function. Again, this one is not in your book. I'm not sure why, but is globally function f of x, function f of xy is globally if it is continuous at every interior point. Oh, that's the xy domain, xy plane. Good. So the function we just had is not globally continuous. The one before that is globally continuous because it's continuous. So you can check the continuity at a single point, because sometimes that's all you need, continuity at one point. Sometimes that's all you need, and that's the 3 rules. But sometimes you need, most of the time, you want to know the continuity of the whole thing, right? Because it's a 3D shape that you can pick up. So now, we also have another definition. You can switch the color to blue, I guess. And this theorem, sorry, for composite functions. So, continuity of composite functions. And we have, if u equals g of xy is continuous at point AB, and z equals f of u is continuous at g of AB, then the composite function z equals f of g of xy is continuous at AB. Standard, same as in your Calculus 1. If you add continuous function, subtract continuous function, divide, multiply, square them, square root them, all of the operations done on your domain, your denominator needs to be such that it can't make 0. So the only way when you really have to be careful is when you have a situation when you're combining two functions through division and denominator can make zeros. That's a problem. But if denominator is different than 0, you are again dividing two continuous functions, you will get the continuous function. And the last one is the function composition. So in Calc 1 we had the function of one variable, so we say if the f and g are both continuous, then f composed with g is continuous. Now we just, instead of using f and g, we're still using f and g, we have the u and z. So z equals f of g, again, is a continuous function. So absolutely the same as your Calc 1. Now what are the examples? Well, you're just looking for continuous functions. If you have something that is composite, let's say sine of, let's just make it bad, like ln xy. How about that, right? Sine of ln xy. Well, xy is continuous. Those are polynomials. ln of xy continuous. Sine of x is continuous, therefore sine of ln is going to be continuous. So this is continuous. It's continuous because of the theorem, right? And we know that you can write, if you need to, you can write underneath sine is continuous, ln is continuous, therefore the combination of the two is continuous. That would actually be proof, and you are calling upon this theorem. And all of this, which we said, is going to extend to whatever amount of variables and dimensions you bring to the table. So if you have a 27-dimensional space, your domain is going to have 26 dimensions, right? You use all of the letters of alphabet, A, B, C, D, E, F, G, right? So your point will have 26 dimension, right, letter, and then you will use whatever letter for the main, for the dependent variable, which is in our case was z over here. Here I'll lend you one of Serbian letters, sh. There we go, sh. So you can say sh equals, and then f off, and you put the 26 letters from this alphabet into it, and there you go. Great, we are done. This 12.3 is done. After a whole week of working on it, it's done. Bye.